me if you want to be polarized.
In this video, we're looking at polarization. The science understanding for today's lesson is listed here, again, straight out of the SACE expected knowledge. Polarization. So you've probably heard of the term in terms of sunglasses, one of the most commonly used terms, but there's a strong physics application. It ties in with this electromagnetic wave stuff that we're talking about. So the image that you can see there is an example of how things will look between a non-polarized filter and a polarized filter. And we're going to talk about how it actually works with that electromagnetic spectrum or the electromagnetic wave. So if we go back a step, let's look at radio and television signals. An antenna is used to transmit or receive these signals. They're usually made up of aluminium rods, and this converts an electric current into this EM radiation and vice versa if it wants to send the signal. The antenna is designed to transmit and or receive within a certain frequency range. It's not much good if we're trying to send phone reception or a TV signal and we're picking up all sorts of other things. They need to be tuned to a specific frequency. The simplest type of antenna consists of two metal rods, which is known as a dipole antenna. The monopole antenna consists of a single rod. It's just a vertically placed single metal rod. It looks pretty average. A really common example of that is what you see on the front of people's cars with things like UHF antennas, radio antennas. They're just a single piece of wire sticking up. Often they're a fiberglass wire with a metal casing, things like that for the UHF. It's just a vertical rod, right? So that would be an example of a monopole antenna. The antenna mounted on vehicles is exactly that. So sometimes they'll put them on the metal roof, and this can serve as a ground plane. So it can kind of create a larger plane within that spectrum. In general, all antennas work on the same principle. So the concept of polarization was covered back in stage 1. Again, some of this will be a bit of a recap, but plane polarization involves the restriction of the vibration to a single plane. Rather than it oscillating left and right, up and down, probably at every other angle, we kind of restrict it to a single plane and we focus it, or filter it is a better word, in that plane specifically. So for a radio and a television signal, we produce these waves when an electron is forced to oscillate within the transmitting antenna. And we can see that down here. So we push it up, it creates this arc, and then as it's pushed back down, it drops and creates this other arc. And if we repeat this process up and down, it's exactly how we oscillate a wave. Since the electrons can only oscillate in one plane, which is the up and down motion of that antenna, the waves are going to be plane polarized. So we say that they're plane polarized, which means they're only in one direction. So if the antenna was horizontal, the wave would be going in this direction towards you, and it would be plane polarized in the horizontal direction. So the antenna is what dictates the polarization of the signal. The EM wave is polarized in the same direction as the vibrating charge that creates it. So we're restricted by the antenna. Conversely, the antenna is only going to receive the waves that are in the polarized direction as it. So if you've got a vertical antenna, it's only picking up waves in that direction. If you've got a horizontal antenna, same thing. So from last lesson, we talked about the plane of polarization is the electric field, as this is the generated field parallel to the antenna as a result of that moving charge. So polarization is electric field. Only an antenna oriented in the same direction is going to receive that signal, again because of that polarizing direction. Electrons in the receiving antenna are forced to oscillate by the electric field that's coming in. So we've oscillated the object, we've created the wave. As the wave comes in, it hits this receiving antenna electron and it pushes it up and down with the wave. That then induces its own sort of signal, its own sort of wave within the antenna, and that's what we get as our signal. So if there was a TV channel in the country that was different to the city, the reception from one could interfere from the other. We don't really want to be, I mean maybe you do, we don't really want to be tuning into Northern Territory TV when we're sitting at home in Adelaide. So, or even maybe less extreme, we don't want to see the weather report for Cooper Pedy or something like that when we're sitting here, because for most of us, we don't really care what the weather at Cooper Pedy is. But also it would just interfere. So it may create static, it may reduce the quality of our signal. So that's a problem. So how would you fix that? Based on what we know about this polarization concept, how might we actually fix that and not interfere signals? It's all about polarization. So I don't know if you've ever noticed, but if we horizontally orientate the antennas in the city and vertically orientate the ones in the country, there's no way that we can pick up each other's signals because they're 90 degrees out. And this is actually what we do. So in the city we have horizontal antennas. You'll often see the ones that stick out. And in this country, they have the vertically orientated antennas. Maybe not for your generation, but if you've ever seen, especially if you've seen on TV and things like that, these old little two-prong antennas, they were just two telescopic wires, basically like a dipole antenna, and you used to have to get them and sort of fiddle around with them and shift the little prongs apart and together and rotate it and jiggle it around just to find the sweet spot to get really good quality TV reception. What you were actually doing, if you've ever done that or you've ever seen it in the movies, is you were actually trying to orientate your antenna to the polarization of the signal. So if you were flexing those to an angle, you were trying to find the sweet angle at which you picked up most of that signal. If it was out a bit, you've lost some of that signal and you haven't got a really clear either image or audio. So this is a little video about polarization, and then we'll come back and I'll show you some examples of a polarizing filter.
The light from a light bulb or from the sun has electric fields oscillating in all possible directions. But you can aim that light through a filter like a vertical slit so that only one kind of polarized light can pass through. In the case of a vertical slit, it will only let light through that's vertically polarized. That is, waves whose electric fields are oscillating straight up and down. And if a light wave is horizontally polarized, then it won't be able to pass through the slit. This is basically how polarized sunglasses work. Unpolarized glasses only use darkened glass to absorb some of the incoming light. But polarized glasses have lenses that work as vertical polarizers, blocking out all light except those whose electric fields oscillate up and down. This is particularly helpful when you're on or near the water. When sunlight reflects off water, each reflected ray is partially polarized in the direction that's parallel to the surface it reflected off. So when reflecting off flat water, the reflected ray becomes partially horizontally polarized. And since your fancy sunglasses only let in vertically polarized light, your eyes are protected from the glare that comes off the water.
Okay, so just before I leave you there and we have a look at some of these questions on polarization, I've got an example for you. So in my hands, I've got two polarized lenses. So how this works is that they've basically got tiny little slits cut into them, or filters in a certain direction, almost like minuscule little parallel lines. So that's going to block anything that's coming up and down because it's smashing into those lines and it's not getting through. Anything that comes horizontally though can pass through those little gaps and keep going. So an example of this is if I put my filter in front of you, I just suddenly look really tanned. But if I now take two of them and put them in front of you, again, I just kind of look really blurry and tan. But if I start to rotate both of these polarizing filters, you see I'm starting to vanish. And now I'm completely gone. So if I tilt them back again, I'm about 45, and now they're parallel again. So all I'm actually doing here is, if you see, like, look at me, I'm not there, I'm there. So what I'm doing is I'm taking two filters and I'm rotating them 90 degrees, and it's like saying, well, I'll cut out the vertical and then I'll also cut out the horizontal and there's nothing left. So this creates a perfect block out of light. And if I shift it, I can get some percentage of light depending on how much I want. So the most basic polarizing lens, which you often have in your glasses, is horizontal. It's probably vertical, because you don't want the light bouncing off the beach to come up and hit you. So it filters that out. There's no good having two that are perpendicular because I just can't see anything. But I may want some sort of angle where I get a limited amount of light, so it's very tinted. So this is an example, and we'll play around with this in class. This is an example of polarizing filters and what they can actually do, and you can see it. Magic.
Tell me pretty lies, look me in the face, tell me that you love me.